This second part of 9.1, we're going to look at some of the exceptions to the rules and some more challenging structures that we than we looked at in 9.1 part 1. So the first thing to look at is something called a coordinate covalent bond. And this is a covalent bond in which one of the atoms contributes both of the electrons in the shared pair. So for example, when we look at carbon monoxide, we can see that carbon contributes 4 valence electrons and oxygen contributes 2. And we can see naturally where we would get a double bond to form. However, this structure doesn't work because carbon doesn't have a complete octet. It only has the 4 electrons involved in the bond and then this 5th and 6th electron. So that structure doesn't work. And so what will happen in order for carbon monoxide to form is that oxygen will take one of its unbonded pairs of electrons and contribute that to make a third bond. So we have this triple bond. And now both carbon and oxygen have their 8 valence or complete octet, and there are the 10 valence electrons present that are involved in this structure. So one of the ways to kind of think about this when you start to draw these structures now is to think of, all right, so carbon, we get 4 valence electrons plus the 6 from oxygen, so we have 10 total valence electrons that have to get placed. And so if you have carbon and oxygen, you know that for sure 2 of them have to go in between. So we have 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10. And so you've got your 10 placed. And so what you might think of is that, all right, so carbon has its 8 valence or 8 octet. However, oxygen does not. So you could take 2 of these and put them in between here because they're still on carbon, but now it also helps out oxygen. And so but oxygen is still only has the 2, the 4 in the bond and the 2 from the unbonding pair, so they're still 2 short. And so you could take another pair and place it in the middle, and they stay on carbon, but they also help out oxygen. And so a way to think of this, I guess, is just creating a pool of electrons from those valence electrons that need to get placed, and then just taking them and using them so that your octet gets satisfied and you use all 10 of them. Our next little complexity here is when we deal with polyatomic ions. And a polyatomic is a group of covalently bonded atoms that carries an overall electrical charge. So we worked with polyatomics when we did our ionic bonds. And it's really polyatomic ions bond ionically. However, the bonds within a polyatomic are actually covalent. And so when we have a polyatomic and we're drawing the Lewis structure for them, we have to place them in brackets. As you can see here, we have the brackets, and we indicate the overall charge. So when you figure out the total number of electrons, when you do or have a polyatomic that you have to draw the structure for, so here this structure would be for NH4+. We know that nitrogen gives us 5 valence electrons, and the 4 hydrogens gives us 9. So there's a total of, for a total of 9 electrons. However, this plus sign indicates that we lost 1 electron. And so that has to get reflected in our diagram. So we lose that 1 electron. And so our diagram needs a total of 8. And if you count through, we have 2, 4, 6, 8 electrons. And so that charge has to get reflected in the total number of valence electrons. And so that's when you have those polyatomics. I guess you will, when you're drawing these structures, if you have a polyatomic and you forget the brackets or you forget the charge, there will be a point deduction on your assignments and quizzes and tests. So you need to be diligent when you're drawing those. So some of you have come across different ways to draw these structures, but almost always there's one correct way. And a way to figure that out is by looking at formal charges. The formal charge is the number of valence electrons on an isolated atom. So this looks at one atom in a compound or in a Lewis structure, minus the number of electrons assigned to that atom. So we have the formal charge formula, Fc for formal charge. You take your number of valence electrons minus the number of lone pairs minus the number of bonding pairs divided by 2. And this is used to determine the most likely Lewis structure. So we'll practice this formula. It's actually pretty easy for how long it is. And so you want your overall formal charge to equal 0 for the most likely Lewis structure. The only difference is if you have a polyatomic, your overall formal charge has to equal the charge of the polyatomic in the most likely structure. And so we can practice. When we draw CH4, we know that carbon has 4 valence electrons plus 4 times 1 from hydrogen for 8 electrons. And so carbon, 1, 2, hydrogen, 3, 4, 5, 6, and 7, 8. And so when we look at just one of these hydrogen atoms, we take our formal charge equals the number of valence electrons minus unbonded electrons minus bonded divided by 2. So for hydrogen, hydrogen has 1 valence electron. It's in that first family, so it's got 1, minus, in this particular diagram, it has 0 unbonded pairs. And we have 2 bonded electrons, but divide that by 2, so that gives us 1. So 1 minus 0 minus 1 equals 0. So we can write the formal charge in little parentheses by that hydrogen. And now instead of calculating the formal charge for the rest of these last 3 hydrogens, because they're all symmetrical, all of those formal charges will be the same as that first hydrogen of 0. So then when we look at carbon, carbon has 4 valence electrons. That particular carbon has 0 unbonded electrons, and it has 8 bonded electrons, but we divide that by 2, so it's really 4. So 4 minus 0 minus 4 gives us 0. So the formal charge on that carbon is 0. So when we look at our overall formal charge, we have 0 plus 0 plus 0 plus 0, 0 plus 0 plus 0 plus 0, plus this final 0. And like I said, you want your overall formal charge to be 0. And so this is the correct structure for CH4. So if we were to draw the Lewis structure for sulfate, sulfate has a formula of SO4 2-. So this is going to allow us to practice drawing the polyatomic because it has the charge, and we can check out the formal charges to make sure our structure is correct. So sulfur has 6 valence electrons. Oxygen also has 6, however there's 4 of them in this particular compound for a total of 24. And so we have a total of 30 electrons that need to be placed, but we also have to factor in this charge. This -2 tells us that we have an additional 2 electrons. So we really have 32 electrons that need to get placed. So we have a total of 32 electrons. And so we put sulfur in the middle. And sulfur needs to have its octet satisfied. So then you place your 4 oxygen around it. And then those each need their octet satisfied. And then the last step here is to make sure that you've got all 32 electrons placed. I kind of do a little shortcut here and say, all right, here this oxygen has 8. And there are 4 oxygens that look exactly like that. So 4 times 8 is 32. So, yep, we have all of our all of our electrons placed. Because it's a polyatomic, you need to remember the brackets and to write the charge outside. And so now we should check our formal charge. So remember, formal charge says your number of valence electrons minus the unbonded minus the bonded electrons divided by 2. So in that oxygen that I've got boxed in blue, oxygen has 6 valence electrons. There are 2, 4, 6 unbonded electrons. And there are 2 bonded. 2 divided by 2 for 1. So oxygen equals 6 minus 6 is 0. Minus 1 gives us a -1. So this oxygen has a -1 formal charge, as will all of these because they have that symmetrical shape to them. They're all the same. So right now we're at an overall charge of -4. That's not okay because our overall charge on that polyatomic is -2. So we need to look at the sulfur's formal charge. Sulfur has 6 valence electrons. In this diagram it has 0 that are unbonded. And it has 8 bonded electrons, which is 8 divided by 2 for 4. So 6 minus 0 minus 4 is a +2. So when we're looking at our overall charge, the -4 plus 2 breaks down to an overall charge of -2. So yep, we have our correct structure because this charge matches with the charge of the polyatomic. Resonance structures are other things that we often see with polyatomics. Right here, many polyatomics will demonstrate resonance structures. And this is the use of one or more Lewis structures to represent the covalent bonding in a molecule. So for example, ozone, which has 3 oxygen molecules bonded together, can have this first drawing. And what you'll notice here is that the double bond is between, let's call this the first and second oxygen. But there's no rule that says it has to be between that first and second, because it could really actually go between the second and third, as this structure is the second structure is showing you. So when you report or draw the resonance structure or the structure for ozone, you have to draw both possibilities. And you separate them with this double-headed arrow, which really means like or. So we're saying this, we could have this Lewis structure, or we could have this second Lewis structure. And so you need to worry about resonance structures when you have at least a minimum of 1 double bond and 1 single bond in the same structure. So this is showing that minimum. We have at least 1 double bond with 1 single bond. And so the true structure of this ozone, or any resonance structure, is the average or a hybrid of all of the possible resonance structures. So down here we have NO3 minus. Is also a resonance structure because we have 1 double bond, and in this case we have it paired with, or there's 2 single bonds in this structure as well. And so what you'll notice the difference in all three of these resonance structure is the location of that double bond. It starts off at the top, then it moves down to the bottom left, and then lastly to the bottom right. It's exactly the same structure. The only thing that changes is the location of that double bond. And that double bond can only move to a location that has it bonded exactly the same way as it would in that original spot. So here we've got it bonded to an oxygen and a nitrogen. Same down here, an oxygen and a nitrogen. And the last spot as well. They're exactly identical, except the only thing that changes is the location of the oxygen atom. And so resonance structures you can have 2 like you do here, 3, and some of them can even have up to 4 possible resonance structures. And so if you have a resonance structure that needs to be drawn, you need to have all of the possibilities drawn, or you will lose points as well. So these are my personal favorite rule breakers here. And these are the exceptions to the octet rule. We can have either incomplete octets, odd electron molecules, or expanded octets. So an incomplete octet is exactly that. It is an octet that has fewer than 8 electrons in it. So beryllium, boron, and aluminum all can be short on this octet rule. Beryllium is really small, and it makes covalent bonds, even though it is an alkali earth metal. So beryllium has 2 valence electrons, and so when hydrogen bonds to it, the 2 hydrogen atoms can just bop into the 2 openings right there, and that compound will be satisfied, even though beryllium doesn't have 8 electrons. Boron and aluminum also can play by this rule here, and not achieve a full octet. And so BCl3, notice each of these is 2, 4, 6 electrons, and so boron has an incomplete octet. And again, that is okay. So the 3 you will have to memorize that beryllium, boron, and aluminum are the 3 elements that break this octet rule and have incomplete octets. Nitrogen is another rule breaker here in that it can have an odd electron. So it's not possible for all the atoms to achieve an octet. So nitrogen has 5 valence electrons, and so sometimes it's hard for it to get paired up, that 5th valence electron. And so you will see that it gets only 1 electron. It's unbonded and unpaired, which is, in the other video, a very bad thing. But here it's much more common, not common, but it's okay when it happens to nitrogen. And the last exception here is expanded octets, and this is where elements can hold more than 8 valence electron. This happens in elements of the 3rd period or higher, because now that D sublevel becomes available to make extra bonds or to hold extra electrons. Again, you'll want to memorize that phosphorus and sulfur are 2 elements that can react with halogens to make stable compounds in which the central atom has an expanded octet. So many times when we deal with expanded octets, you'll see the element that can expand its octet in the middle, and then the other elements will kind of circle around it and expand it. So in that phosphorus example, phosphorus has, 2, 4, 6, 8, 10 electrons in it, and that's okay. Again, sulfur here, 2, 4, 6, 8, 10, 12, and it can expand its octet very easily. So all of those are valid structures. The last thing to talk about today is bond energy. This is the energy required to break a covalent bond. High bond energy equals a strong bond, in a very stable molecule. So halogens are all naturally occur as diatomic molecules. So remember chlorine, it's chlorine bonded to chlorine, bromine bonded to bromine. Those are all diatomic molecules. Actually, all of these are all diatomic. And these are requires a relatively small amount of energy to break those bonds. And you can see that compared to like hydrogen's diatomic bond here has 436 kilojoules per mole of bond energy. So that's very, very strong bond compared to like the iodine bond here. It only has 151 kilojoules per mole. So that's a fairly weak covalent bond and could easily be broken. So this was just a look here at some of the more complex Lewis structures that you're going to come across.